Good morning, those of you who are online. Oh man, Haley, your picture for a minute looked like you were staring really intently at the camera, and then it was frozen. I didn't realize it was a picture. Weirded me out for a minute. Okay, don't forget to do attendance. It is now open. Does anybody need me to do it for them?
Yes, please.
Yes, please. Okay. Anyone else?
Yes.
Yes. Okay. Got it.
How many minutes is it open?
So present and online are open for 5 minutes, and then after that, it's late is open until the end of class. And if you don't do it, it automatically marks you as absent. Which you can always send me an email and say, hey, I was there and I had problems doing the attendance. I'm fine with that and adjusting it. But I wish it would open a little before class too, though. I don't know if I can change that or not. So I figured out why YouTube is not letting me stream the lectures there. Apparently, remember I told you last semester it flagged the video for copyright? Well, apparently a second person tagged that same video as copyright because of the song that played in the background. And so they extended how long I can't upload. It's supposed to be resolved in December. Now they're saying until February. So I appealed that. And right now I'm just uploading the recordings instead of live streaming them. Hopefully we'll fix that soon because Tom and Christy both also want to stream their classes to the YouTube channel. So we'll figure it out. We'll see what happens. But for right now, I'm just uploading the videos there because then I don't have to go into each class and Noodle upload it there. I can just upload to one place. So the videos will be up there. They'll probably be a couple days behind because I'm going to sit down and upload them all for the week at once. So you can still have access to the lectures. Just it'll be a couple days behind instead of instantaneous. Any
I have
questions?
I have
Yeah,
a
go
question
ahead.
for the class. For the worksheet that's due on Sunday. Are you going to answer any of the questions off of there, or do we have to come to you if we have any questions during your office hours?
The one that's assigned on Thursday of this week,
No, it's the calculation problems.
the basic fission calculations.
Yeah.
Yeah, we're gonna do some of those today. We're gonna do some of those or very similar ones Thursday. I would really recommend that you guys do look at it before tomorrow though. So if you have ones that are like specifically, I have no idea what this is talking about, I don't remember her saying anything about it, you can have those questions ready in class. But we will go through several similar examples between finishing up binding energy today and talking about fission energy tomorrow. Does that answer your question?
Yeah.
Okay. Okay. Let's share the screen. Okay. Any other questions before we jump into where we left off? Okay. All right. So we were in the middle of using this equation at the end of class and over the end of class. So we're going to go through the whole problem again. And then we're going to have you guys do some stuff on your own, just to make sure we have how this works. I was talking to Cattell in my office, and a lot of this stuff we're going to do in the first 2 weeks is going to be built on as we go through this semester. So I'm totally fine with going a little bit slower at the beginning because I want you guys to really understand this, because then all the rest of the theory You might use all of it if you're a control room operator. You might only use parts of it if you have a certain auxiliary position. But if you understand this, whatever you need to learn specific for your facility, you can pick up in training much faster. So we need to understand how these interactions occur, where all this energy is coming from, kind of the mechanics behind our reactor physics, and then the rest of what we're going to discuss kind of flows easier if you understand these principles. So, somebody tell me what they think the definition of mass defect is. Tell them and we'll come over here. So you were about to speak. Go ahead.
Okay, I'm gonna try. My understanding is that you have these particles in the nucleus, and if you take them apart and you weigh them, the difference between that and if you group them all back, there's a difference when they're all together, and that difference is mass defect.
Okay. What were you going to say, Joe?
Same thing.
Okay. Jennifer?
Yeah.
Okay. That's a good way of saying it. When you take each particle and you look at its mass, you're going to have slightly more than the whole atom together. If you have slightly less, you're not going to get energy out of that atom. And there are some atoms where that is the case. None of the atoms that we care about putting into the reactor are going to have a negative mass defect. Your answer will always be positive if it is an eligible fuel material. Okay. So I know that the bottom gives you the answer here, but I want you guys to find it in your chart of nuclides. Okay? This symbol right here can also sometimes be written like this, right? Just mass defect, okay? We're going to look at uranium-235. What's our Z number?
92.
92. Without looking here, someone look in the back of the book and tell me what is the rest mass of a proton? Jack.
1.007276.
Yes. And what is the rest mass of an electron? Someone other than Jack? If you need to borrow a chart of nuclides, there are a couple on the shelf there. You didn't bring yours.
So I have a question.
Yeah.
The mass of protons, the mass of neutrons, and the mass of electrons, is that always the same AMU number?
Yes, this is a constant.
Okay.
That's why it can be in that list of constants on the very back page of your chart of nuclides, because the rest mass of that does not change. Does anyone know why?
Sorry. In the calculation, when you do MP plus ME, why wouldn't you just put the sum of both of them instead of?
You completely can. The reason I pull it out is so you understand we're adding up every single particle that's in the atom and comparing that to the whole atom.
Okay.
Right? So I'm just making that difference of what we're doing very clear. If on your crib sheet you want to write mass of a proton plus mass of electron as one value, totally fine. Okay, but again, without looking here, someone finds from the chart of nuclides, what's our mass of electron, rest mass?
0.000548.
Yes. Okay. What is the A number for uranium-235?
235.
235. Okay, and what's 235 minus 92?
I think 143.
Okay, and someone finds mass of a neutron. Eight, six, seven. Yeah. So you guys can kind of play around with this if you want, and you'll notice that if you round too much, you'll get an answer that's almost zero, because these are very, very small particles. And so what we're dealing with, hey Kyle, is these significant numbers out here. So I would encourage you, like as you're doing the worksheet, to do the calculation a couple times and see what happens when you round. And know that I'm going to want to see on your answers at least 4 significant figures. Because we might have too much rounding, we'll get very different answers and it won't be right. Because we're just dealing with stuff that's so small. Okay, what's the mass of your uranium-235 atom? So out to 4, what is it?
3924.
3, 9, 2, 4. So keep at least 4 for these types of calculations, okay?
But I thought significant numbers also started from the front too.
They do. For real significant figures, yes, they include all the
You
numbers.
just want 4 behind
I-
the decimal.
I should say it more correctly. Carry it out to 4 decimals. Thank you, Kyle. Be technically correct. So 4 digits of decimals. Okay. What is our mass defect for uranium-235?
So I know yesterday you got 1.91517, but every time I do it on my calculator, I get 2.71858.
Okay. So let's look at why. Because there's like 4 questions on that worksheet, and I want to make sure that you guys have this down. So let's put in a new section. Hey, Porter. Let me pull this up where we can do the calculation together on the screen.
We should go a little slower too.
Okay, I can do that.
Sorry.
All right, so our equation here mass of a proton, mass of an electron. What's the next term?
plus your A. So
Yep, A, and then what, Haley?
minus the 92 or the Z number
Right? And then,
times the mass of the neutron, which was the 1.008665.
yep, and then all of this is going to be minus our total mass of our X atom, right?
235.043924.
Yeah, okay. So, we're going to find, actually, let me switch colors here. We're going to find the mass defect of uranium-235.
Can you
Okay.
share the board?
Oh, I'm sorry. I thought I did. Yes, I absolutely will. There you go. Sorry, Haley.
Thank you.
Okay, so when we have an atom, right, we have our A number here and our Z number here, right? So if this is uranium-235 and our Z number is 92, right? You guys remember that structure when we talked in materials about basic atoms? Okay. So given that, we're going to have 92. And someone go ahead and add for me, what is the mass of a proton and the mass of electron together?
1.007826.
I didn't calculate this myself. Can someone confirm that's what they got too?
Yeah.
That's what you got? Did you get a different number, Lynette?
She rounded.
1.0078085.
Okay, let's see. All right, so I get 1.00783. So Haley's number is pretty close there. I think I just my calculator rounded at that fifth number. Okay, that plus 235 minus 92, which was 135, right?
143.
143, that is correct. Okay. And our mass of a neutron?
$1.008665.
That is correct. And then this will be minus our mass of uranium-235, which is
5.8439.
so when we are doing order of operations, you're going to multiply the 92 times the 1.00783. What is that number?
92.719992.
Say that one more time, Haley.
92.719992.
9992. Okay. So that is that plus 143 times 1.008665. What do you guys get for that number?
237.76255057.
So I think you're making a mistake there, because if I multiply 143 times 1.008665,
Okay, that's where it was.
I get a 144, 2, 3, 9, 1. What Kyle got. Can you get that number?
144.239095.
And then we're going to subtract again. So that is, oops. That gives us that number. And we move this number down, right? This is not an equal, that's just a subtraction. 235. Now add and then subtract. So add the first two numbers and then subtract the 235.
Okay, I got it now.
Okay.
$1.915163.
And I'll just do 4 digits there. Okay. Did anyone else not get this answer?
So I got it. I was just gonna ask you if rounding's okay.
Okay. Yeah.
1.91.
At that fourth digit, we can round.
Do you have to?
Where are you guys getting the mass of the electron? Or is that up on your PowerPoint?
It was on the PowerPoint, but don't rely on that.
Oh. Rest. Okay. So what is the rest mass?
So that's a good question, and I was going to explain that next.
Okay, sorry.
No, that's great. That's perfect. What was your question, Joe?
Oh, just a rounding thing. 1.914922. Is that acceptable? Do you want us to always do 4 digits and just be standard? Or I probably asked you that yesterday even.
4-digit standard, yes. Do you need?
On your key to B231,
Yes, it is on my desk.
take the label.
Yes, it's the purple little dangly thing that says Rad Lab.
Okay.
And then there's a purple cover and a blue cover. One opens the actual lab and one opens the door to Jeremy. Okay, so the reason I want 4 digits is so that when I grade, at least these first 2 should match my answer. If you round to 2 digits all through the equation, 2 decimals, sorry, right here we're going to get different answers. So if your third and fourth decimal are different than mine, that'll be okay. But make sure that you are not rounding less than this until your final answer, or we will have different numbers here. And the numbers are so small that differences here do matter for our equations. And I will take points off here. So I'm telling you, keep at least 4 digits. Don't round until the end to 4, so that I can give you full points if you did the math right. Because in this scenario, rounding errors and rounding too soon changes the answer. We're dealing with such small particles and such small phenomena that rounding changes the answer. Does that answer your question?
Yeah, I was on another one.
Okay.
But during the calculation of the problem, you want the digits kept long, like you've got 6 digits.
That's gonna make your answer more correct.
Well, so when you're doing the problem, you want the longest number possible and then round at the very end and not any other way.
You will have the most correct answer if you don't round at any point until the end. Because I know some of you like to do a lot of your work out by hand, and that's good for me to see each step. I can give you more partial credit. Writing 6 or 8 numbers a bunch of times can get old. So I'm saying if you show me steps with at least 4 digits, we're going to have at least the first 2 that match on our final answer, and that's what I'm going to grade. If you choose to put more, that is just more levels of accurate. Does that make sense? Okay. All right, let's switch back to the slides and answer Kyle's question.
Yeah, I was looking at it and it's still lost. So I need to go back to, was it Tuesdays?
Yes, we are continuing from slide 17 of Tuesday's lecture.
So like, I see how the numbers are close, you know what I mean? From where we went in this equation.
This equation, is this what you're still confused on?
No, yes, I mean, yes, but like, so the mass of the proton, mass of, from what you just showed me, is that different?
So in your chart of nuclides, there's two values given, two different units,
Right.
right? So, I think the first unit is kilograms. So like the proton rest mass, 1.672621 e to the minus 27 kilograms.
Yep.
Next, it's 1.007276 e to the 0 u. That u is for atomic mass unit. When we do these calculations, we're going to be using atomic mass units.
So, going to the problem that we did, the protein, or the proton rest mass was 1.0702776. We're using 1.007826.
Now, that 8 number is for the mass of the neutron. 1.007277, they rounded, is proton. 1.008665 is a neutron.
Right. Okay, I don't think we're following. The numbers don't match up in my head. I'm not doing that. That, so,
I don't understand what you're doing.
so that mass of a proton is 1.007277.
So you,
Is that not the number we just did?
I think that you times that. That number should be the one from here or off the slide.
277. Okay.
Yes,
Okay.
I think you just
Just call it.
wrote the wrong number.
Okay,
Just so
so-
you know, this is 97, this is swap. 8597, 859. Not following that sheet, but it might be.
Okay, so Cattell says that the DOE handbook made a little transcribing error and that 9 and 7 are switched in your chart of nuclides. The chart of nuclides
Mass of
is going to be the right thing.
That's the left on our PowerPoint, that's different than what this book is.
So those of you online, did you hear that? Cattell's pointing out that apparently the DOE handbook that I took a screenshot of here, this should be 8579 according to your chart of nuclides. The chart of nuclides is going to be correct.
85799.
Are we gonna get that, or that's possessed, or do we have to memorize it?
You can have a one-page crib sheet, and most likely you're also going to be allowed to have your chart of nuclides.
So
Yeah.
here, the E, so on the mass, or the electron and the rest mass, it says E to the negative 04. So that's just telling you your whole number is going to be to the negative.
Yeah, so in the chart of nuclides, I think it's written as 5.4859 e to the minus 4.
Right.
These extra zeros are just moving that decimal point 4 over.
So what's the 23 for, or like the parentheses on the side of the, does that make sense? Is that valuable?
Okay, so that is being taken out to so many digits.
No.
The scientists who did this measurement are now telling you where their rounding errors are. We're dealing with quantities so small that even our standardized tables can have errors.
Okay,
So the parentheses, that's where they think their error starts. So they're really confident with this number, but then when you get down to the last few digits, those are still the digits, right? Or the 2, 3 here, but that's where they think they have a rounding error. That's what they're saying. Kyle asked why it says rest mass. So we talked about the fact that we're looking at this mass, and this mass defect is going to be what we convert to energy when we start fissioning, right? When an atom is moving, which it does whenever it has thermal energy, right? What law of thermodynamics is it that things at absolute zero have no kinetic energy?
Is it, 3 or the zenith? 0.
Zero. It's the 0th, right? When we get to absolute zero, things stop vibrating with internal energy. They don't have energy. That is when we have only mass. Some amount of what's in the atom is energy. And so if you're trying to measure the mass as something is moving with energy, because mass and energy are equivalent, just different forms, you're going to get a wrong answer. So scientists are trying to measure these particles' masses as close to absolute zero as they can get. And then we have a little bit of error in our digits, indicated by those parentheses, because we can't actually get absolute zero for a lot of our stuff, our materials, right? So rest mass means they're giving you purely mass. There's no energy in that, which is why we have a difference between the sum of our rest masses and the mass of our whole atom. And that's why we can exploit it and have nuclear reactors.
So that's the mass lost in energy.
That's an okay way to think of it. It's not actually lost unless we do something to pull these parts apart, right? It just sits in the atom as long as the atom is constructed. It might be lost in a chemical reaction. It might be lost in a nuclear reaction. And it's definitely going to be lost when we split this atom into its parts through fission.
So just excited atom.
It could be ground state. Having this energy doesn't necessarily mean it's our chemical definition of an excited atom. It could be a ground state atom. It just possesses that energy. So think about that energy as like, this is kind of graphic, but I had a professor who explained it this way and it's always stuck with me. Think of that energy as the blood in our body. The blood's in our body, but if you start pulling your arms and legs off, you've got the parts, but the blood is lost, right? So that energy, when your whole is there, you may not be excited. And when you start pulling things apart, then you can release that energy. So kind of gross and gruesome, but I mean, you remember it. Does that answer your questions, Kyle? Okay. So we just did this calculation, right? And we got that answer. That is mass defect. Now, in like our analogy of the body, if there's this extra energy that's being held in an atom, like the blood in our body, why doesn't the atom just break apart? Why does our body not just break apart? And the answer is binding energy. There's a certain amount of energy that we have to supply in order to manage to separate the particles within an atom. This energy that you have to supply to do that is the same as the amount of energy released if you took those separate particles and formed an atom. Okay, so our mass defect converted to energy is our binding energy. So these are the same thing, but one will be in units of mass and one will be in units of energy. So binding energy is the energy that's held in an atom based on the quantity of its mass defect. So they're the same thing. They're that amount of stuff that we can extract whether it's described as energy or mass, which physics says energy and mass are equivalent, right? That's why mass defect and binding energy are equivalent. That's really important. Does that make sense the way I said it? Do I need to state it another way?
It's
Okay.
both the energy that must be supplied to separate the nucleus and the energy that you receive from doing so.
And it is the energy equivalent of our mass defect. So when we calculate either mass defect or binding energy, it is the same thing, but the mass unit and the energy unit of the same concept. Do you have a question?
So, how are figures? Alright, well, I'm sure we'll go through that. I was gonna say, how do those figures calculate the binding energy?
So, we will do that on the next slide. Just real quick, the number of particles in a nucleus increases, usually the binding energy increases. But this rate of increase is not uniform. So when we look at the chart of nuclides, right, and it's at that diagonal and we're going up in the number of protons and neutrons in the nucleus, you're always going to be going up in binding energy, but not necessarily a linear relationship, right? Sam.
What unit of measurement is bonding energy?
That's where I was going.
It's going to be in electron volts, and we're going to do that right now. So, E equals mc squared. What that says in physics is that energy and mass are equal. You multiply the mass times the speed of light. The reason it's important that we have rest mass is that we're not accounting for any of that movement, right? Velocity of light. When we convert an AMU to electron volts, 1 AMU is 931.5 mega electron volts. So whenever you calculate a mass defect, calculate it in AMU, and then all you do is multiply it by 931.5 MeV per AMU, and you will get the binding energy. So, what is the binding energy of uranium-235?
I got 1,784 MeV.
Did anyone not get that number?
What is?
1,784.
Could I see the formula again?
Yeah, I will actually show the calculation so we can look at how we did this. I think there's about 4 questions on your worksheet that are binding energy and mass defect that are all going to be very similar to what we just did.
By the way, I'll go negative. However, every time I come to class, I get a tickle. Real common.
Okay, this part should be pretty easy. We're just converting units, right? Is anyone confused on this part? Haley and Caden, you guys got it?
Yeah.
Yeah, as long as you have the mass defect, it's really simple. You're just converting.
Exactly. Is that making sense for you, Marcus?
So are you ever gonna have one that says find the mass defect and then do binding energy? Is that also?
So that's exactly what we just did. And yes, you absolutely do have questions like that on your worksheet, and you will on a test. Okay. So when we talk about specifically our energy from fission, which is what we really care about, right? Binding energy and mass defect has an effect on every chemical reaction and nuclear reaction that can occur. But we honestly really primarily care about the energy we can get out of fission, right? That's what the purpose of operating our reactors is. So when we have a heavy nuclide, which is key, we don't fission light nuclides. Fusion will happen with light nuclides, right? They shove them together, and that forming of a new atom releases energy. We rip apart a big one, and that's what gives us our fission energy, okay? The amount of energy released by fission will be based on either the change in mass, which can be expressed by the difference in binding energy per nucleon. Binding energy per nucleon is when you take your binding energy, like that 1,784 that we just calculated, and we're going to divide by the total number of nucleons in the atom. What is that number? Is it an A number, Z number? What's the total number? It's the A number. So for uranium-235, if our binding energy is 1,784, what is the binding energy per nucleon for uranium-235? What did you get?
12.48.
That's not what I got.
Got 1784 divided by 143.
What's the A number for uranium-235?
Oh, yeah.
So are we taking the MEV number that we just got and dividing it by the 92? Or the A
No,
number?
that's the Z number. Yeah, we're going to divide by the A number. 7.59, and what's the unit?
MEV.
Still MEV, exactly. One of the questions on your worksheet is going to ask you to compare the binding energy per nucleon to uranium-235, which we just did in class, to that of uranium-238. If uranium-238 has a higher binding energy per nucleon, do you think that's going to say it's a better fuel material or worse? Why worse? Okay. Takes more energy to break apart. Okay. Does anyone think it'd be better? Everyone agree with Jennifer?
Said more particles equals more binding energy. I don't know what that has to do with this.
Okay, it's true. More particles, more binding energy. What do we usually use as our fuel? 235. Why? Go ahead, Kyle. Okay. If, as Jack indicated, you're going to find out that uranium-238 has more binding energy per nucleon, and we use U-235 instead, is it what Jennifer said? Is it because it's harder to break it apart? Because if it has more, and I'm not necessarily saying it does, don't change your answer in your calculation because of what I'm saying. We're hypothetical here. If it has more binding energy per nucleon, wouldn't that say we can get more energy from fission?
But it takes the same more to break it apart, doesn't it?
So if your binding energy is higher, it's going to take more to pull it apart, right? Because you have to supply the same amount of energy to pulling it apart as it's going to release. So it's potentially harder to fission. We're going to talk about this more. I'm not going to give you the exact answer right now, because I want you guys to kind of think about it. But basically, energy release is not the only thing we have to consider when we make our fuel. But I just kind of want you guys to think about that, chew on it.
Probability of fission?
That is absolutely a factor, right? Our cross section for fission, it's a huge deal.
So it's not necessarily the one with the highest MEV.
Yeah, because
So if you have a higher energy release, you also have a higher energy input, right? You have a pro and a con there. What were you gonna say, Jack?
I thought it was because like U-238 is like almost stable, whereas U-235 is not. And so it's just a lot easier to kind of create fission with it.
So U-235 does have a higher fission cross section. It's easier to fission. But we have to put a ton of energy into enriching. And if we get more energy out of U-238, like why do we put the energy into enriching?
Asian U-238 is one of the daughters of plutonium-39.
We produce a lot more plutonium fissioning uranium-238, and that's very unattractive from our safeguard standards. Everything you guys are saying is right. I'm going to ask. Yeah, so non-proliferation is preventing weapons. And so when we produce more plutonium, that's a negative thing for our non-proliferation goals. Everything you guys are saying is right. And I'm going to ask this question multiple times as we go through because there's a lot of different factors that end up putting us at why we have the fuel we do. Yeah, Kyle.
Okay, so why did I take the binding energy 1784 and divide it by 35?
To convert it to the binding energy per nucleon.
Per
And the difference in the binding energy per nucleon between two nuclides is the difference between the fissile nuclide and the fission product, right? So when we take uranium-235 and we fission it and we create xenon something and samarium something, right, that add up to 235, we're going to calculate the binding energy of samarium and xenon and uranium-235. Then we're going to calculate the binding energy per nucleon for those three atoms. And the uranium-235 binding energy per nucleon minus the binding energy for the samarium and the xenon is the energy we can get from fissioning uranium-235 and splitting it into those two fission fragments. Does that make sense? So if fission is a neutron plus uranium-235, and that splits into X fission fragment, and then another fission fragment, plus some amount of energy. We can calculate that energy as the binding energy per nucleon of the U-235 minus the binding energy per nucleon of our first fission fragment minus the binding energy per nucleon of the fission fragment. Have you guys seen the, I think Mike Fort showed you guys the double humped graph, right? The camel toe of fission fragments. That shows you the distribution of fission fragments that you're likely to get. It doesn't matter what it splits into, right? We're going to get roughly the same amount of energy. There'll be some variance. Okay. Just kind of to end, there are a couple of slides on fuel. We're talking about all this energy released from fission.
What's the last number? 235 minus X.
Plus E, that's energy released. And then that energy is the binding energy per nucleon of the fissionable nuclide minus the two fission fragments. And I'll post this on YouTube if you need to look again. Okay. So as we talk about this energy that's released, one uranium pellet, size of your thumbnail, right? Is the same amount of energy you can get from burning 481 cubic meters of natural gas. So a tank this big, this person for reference. A metric ton of coal, 3 barrels of oil, or 2.3 metric tons, 5,000 pounds of wood. So this little tiny amount of mass and energy that we're talking about is actually super powerful as a source of fuel. And that's why we use it, right? Just as a little bit of a refresher, definitions of fissile and fissionable. We did that in the materials class. If you were having trouble keeping them straight, I suggest you look at those and review. And then we have a little bit of discussion on enrichment, which we'll cover at the very beginning of class tomorrow.
Tomorrow's the lab.
Yes, we're going to cover just a little bit of this, and then we're going to do some calculations together. Yep. Any questions online?
Well, I just want to make sure that I got the right answer for this worksheet because I've been working on it.
Okay.
So on number 1, is it barium? The 135 over 53.
Let me pull out a chart of nuclides.
Because at first I'm like, it's lead because I did the 135 minus the 53. And then I'm like, no, that's not right.
Okay. So for worksheet number 1, it is not lead and it's not barium. So our A number is 135 and the Z number is 53.
Oh my God. I get it now. Iodine, right?
Yes, it is.
And then we're going to go over numbers 8, 9, and 10 tomorrow.
So 8, 9, and 10 were supposed to be reviews from chemistry, but if you have a specific question about those tomorrow, we definitely can.
Okay. Because those are the only ones I don't remember going over in your class. But if you're referring to last semester, then I'll just look at my notes from then.
Yeah, that was supposed to be a review to make sure that people remembered that from chemistry. But we can go over it if you need a hand remembering.
Okay, thank you.
You're welcome. See you tomorrow.
However, if I really
Tom's
wanted
lab
to.